Okay, yeah, thanks a lot for inviting me again, and welcome to my talk on consensus dynamics on static and on temporal hypergraphs. I will talk about the static case in the first part of my talk, and then in the second part, I will extend the models that I will introduce to you to the temporal case, temporal hypergraph case. And the work that I will present here is mainly based on joint work with Michael Schaub and Renaud Lambiot from RWTH Aachen University and from Oxford University. Just as a short introduction and motivation, as we all know, and I think we all are jointly motivated by this fact, networks have recently, or not just recently, become very popular to investigate social dynamics. There is only one problem, and that's the main setting that I will talk about today. Sometimes networks fail. So there are certain higher order dependencies in the interactions, for example, group or multi-body interactions, which a pairwise network setting simply cannot capture. And the question then is only when does this become important for the overall dynamics? And in my work, or in many of my works, I specifically focus on social dynamics, such as consensus dynamics. And I will, for this case here, introduce a three-body consensus module to investigate the possible higher order effects of these multi-body interactions. Just already to take this question up front, everything that I'm talking about here is also generalizable to general hypergraphs. I'm just taking the three-body case for simplicity, because then the results are just easier to understand and to illustrate. So dynamics on conventional networks can be classified as pairwise interaction systems. And their agents have local pairwise interactions, and the overall effect of the interactions on each of the agents is the sum of the pairwise interactions with other agents. And in contrast, now we look at the three-body interaction system case, which takes into account the joint influence of triangle neighbors J and K on node I, which is then described as an interaction function Fijk. And therefore, in contrast to the pairwise case, the interaction between node J and K becomes relevant for their joint influence on node I. And our main goal is now to examine if and under which conditions, in the static case, first of all, three-way interaction systems can reveal higher order effects that cannot simply be explained by the pairwise interaction system operated on the underlying network of the triangle structure. And that then obviously becomes relevant for all kinds of applications. So like, when do you actually have to take care of the higher order system underlying? So just as a motivation, in sociology, it is well known that the dynamics in a social clique are determined not just by the pairwise relationships of its members, but often by complex mechanisms of peer influence and reinforcement effects. And yeah, this is captured by this maybe relatable example of joint parental discipline that I show here. So if you look at A, the link between the parents, which can, for example, model a shared opinion or something like that, enables reinforcing dynamics that then lead on to a stronger influence on the child. And that is not captured in the independent pairwise influence in B. So that's just a highlight for when higher order models actually additionally account for the effect of this group as a whole and not just for the pairwise influences. So as I said, in the first part of my talk, I will now talk about those consensus dynamics on static hypergraphs. So let us introduce an interaction function that can actually capture this reinforcing effect that I just illustrated. So it consists of a linear consensus term and of an influence term S of x, or an influence function S of x, which captures the higher order influence of the triangle nodes J and K on node I by basically scaling their pairwise influences by their state difference, which is then modulated by this scalar influence function S of x. So if we assume that S of x is monotonically decreasing, as we can see in the small example here, node P and K, like the node states are there just illustrated by color. So node P and K reinforce each other because they have very similar node states. And in contrast, K and J hinder each other as they are very distinct. And that also models the example of the joint parental discipline, which I talked about before, because parents can either support each other in disciplining a child if they have similar viewpoints, or they can hinder each other if their opinions rather conflict. The interesting thing is now, if you look at this, this function, if s of x is constant, the interaction function is simply a linear combination of the diffusive couplings of the two edges, ij and ik. And the whole dynamics can simply be rewritten as a two-body dynamical system, just after a proper rescaling of the adjacency metrics. So then we're basically dealing with network dynamics. And let's look at that in a little bit more detail now. So if we rewrite the model to relate it to a weighted version of the network Laplacian of the underlying network, we first have to define a weighted adjacency matrix W, and the entries of that matrix account for the higher order effects on the node I over the edge ij. And the weighted Laplacian is then the matrix representation of the nonlinear dynamics. And if s of x is constant, you can see this now there just in the math case, not just intuitively like before. If s of x is constant, that gives us linear dynamics, and this operator is then not time dependent and reduces to the so-called motive Laplacian for triangle motives, which has already been introduced in the literature before. And we are then therefore basically just dealing with rescaled pairwise dynamics. And in the nonlinear case, even if it seems like a reformulation to a pairwise system, the entries of this weighted Laplacian there are dependent first on the node states of the neighboring triangle nodes, so also on the triangle topology. So we have those higher order dependencies woven in this operator on the triangle structure or the hyper-edge structure. So we can conclude that in order to reveal any higher order or genuine higher order effects of three-way interactions, which cannot be explained by the underlying scaled pairwise interactions, we must have nonlinear dynamics. And this general result of our work underlines that a three-edge or hyper-edge topology alone does not guarantee that higher order effects will appear, but it is also heavily dependent on the type of interactions present or the type of dynamics present. And yeah, so what can happen now if this does occur? So if we have nonlinear dynamics, we want to look at that now. So what possible higher order effects may emerge from this model? And we will look at that in three different scenarios. We first apply a mean field approach just to eliminate the topological effects of the distribution of the three edges. And then we additionally take into account certain asymmetric topologies by examining two connected clusters, which represent something like polarized groups. And in the last scenario, we see a joint effect of initialization and topology, which then results in a time scale separation of the dynamics. And just already saying that, keep the setting of scenario B and C in mind, because that will come back or like reappear in the temporal case in a very interesting way. So what are we looking at? Generally, in consensus dynamics, we're interested in if and how a given system reaches consensus, which means that in the end, all of the nodes have the same value. And this property is conserved on undirected networks. And we now investigate in which cases the consensus value is affected by the higher order dynamics in three-way interaction systems. And as we can see here, the average state is only conserved if the weighted adjacency matrix is symmetric for all times. And this is generally true for linear dynamics if s of x is constant, which somehow confirms the theoretical result that we are then just dealing with scaled network dynamics, which we have derived before. And for nonlinear dynamics, otherwise, the symmetry is generally not the case, like does not appear. But it depends on initialization, three-edge structure, so topology of the hypergraph, and interaction function. So that's the interesting case. When do those imbalances occur? And we now want to look at certain cases when those imbalances occur. So in order to investigate how this affects the conservation of the average state, we first consider a mean field approach. So just a fully connected hypergraph. So just all hyperedges are present, no topology shifts in some way there. And remember that the displayed condition there describes when the weighted Laplacian is symmetric. So when the average state is conserved for all times, as we've derived before. And in the mean field, we expect this to happen for an initial node distribution with an average equaling to 0.5. Because as all of the nodes are connected now in this case, the higher order effects balance out initially, and the system is otherwise symmetric because it's a mean field, so like it's a fully connected hypergraph. So this then is expected to hold for all times t. And this motivates the assumption that a biased asymmetric initialization, which is distinct from 0.5, is required for higher order influences on the average state of the system to occur. And yeah, the average state is then expected to evolve in the dynamical process because similar nodes reinforce each other, and then the shift should be enlarged. And the results that you see there are numerical simulations which confirm that. So you can see the nonlinear dynamics on the left side and the linear dynamics on the right side. And yeah, the shift towards the majority in the initial population is present only for the nonlinear reinforcing interaction case and not in the linear one as expected. So that reflects how peer pressure can cause opinion drifts in the population, which would not be present in a network setting. And in the second scenario, yeah, this is an important scenario which will come back later. We now investigate the influence of asymmetric topologies. So in particular, we look at two connected clusters that consist of the same number of nodes. And one cluster is initialized with state 0 and the other one with state 1. And the clusters are connected by a set of triangles or three edges. And we call a connecting triangle between cluster A and cluster B oriented towards cluster B if A contains the majority of the nodes. And yeah, due to the consensus in cluster A, the diffusion now is accelerated towards cluster B. And on the contrary, the influence is inhibited in the opposite direction. And that leads to basically directed dynamics between the clusters, even if the system itself is undirected. And therefore, even if the initial average of the system, because it's the same number of nodes in each of the clusters, is 0.5, and if you remember, that led to a conservation of the previous mean field case, now this asymmetric connection between the clusters leads to one cluster conquering the other, just because of the topology. We investigated that a little bit in more detail. So we defined a parameter P, which is basically the fraction of the triangles directed in one or the other direction of the clusters. And you can see that this perfect shift there in the final consensus value from the value of cluster A to the value of cluster B solely depends on the direction of the clusters. So it's extreme for P equal to 0 towards A, for P equal to 1. And there's also a huge influence on the convergence speed on the system, which you can see in B. So basically, the more directed the connection is, the higher is the acceleration of the dynamics. And which is also interesting is that the simulations show high standard deviations for values close to P equal to 0.5. So that indicates that if the connection between the two clusters is basically balanced, just small shifts by the initial topology can already result in very different, so from like different distributions of the triangles, already in very large differences in the consensus value, which then just average out in many simulations. And this can even lead to some kind of minority influence. So even if this both clusters are not the same size, but one is in the minority, which would then lead to a majority influence in the right case, in the linear case. For the nonlinear dynamics, the minority would even overtake the majority just because of this reinforcing effect of the connecting triangles. One interesting thing is to look at this in a little bit more varied way. So right now we took very extreme initializations, so binary initializations. And if you just take basically uniformly randomly initialized clusters over separate intervals, the same effect occurs, but with a timescale separation. So first of all, the clusters basically, or we observe asymmetric dynamics within the clusters towards their specific means, and then asymmetric dynamics between the two clusters. Okay, so that brings me to the end of the first part, the static part of my presentation. And I just want to take a bit of time to summarize the results so that we can build on that in the second part. So what have we done? We have introduced a new model for consensus dynamics on 3-body hypergraphs. which can be used to show that group interactions reveal higher order effects that are not captured by pairwise network models. But I think what's the most important fact and what's like the takeaway from this part is that we find that nonlinearity is essential to reveal genuine higher order group effects in the static case. So for linear interactions, the dynamics can always be rewritten in terms of a scaled network. And moreover, the higher order effects that result from reinforcing group effects can lead to interesting shifting phenomena. And those can only be understood and described as an interaction of initialization of the nodes, higher order network topology, and the nonlinear interaction function that is present. Yeah, and as I said, this brings me to the end of the first part, the static part, and I just thought that maybe it's a good place to pause and see if anybody has any concrete questions already before we extend this to the temporal case.
Can I ask a question?
Yeah, sure.
Hi, I really like this part that non-linearity is necessary for this higher order group effect. I mean, that seems like sort of intuitive to me in some sense. But my question was like, you didn't take into account any effect of the node dynamics individual. Like you are mostly stressing on the coupling between the individual nodes, how they are linked together. Is there any effect of the individual dynamics of a node? Suppose I put a dynamical system there, would that affect your result in some sense? Basically primarily in the mean field case.
So the dynamic of the variables in my case are the nodes. So I'm not sure what you mean by like the dynamics of the nodes themselves. So if you look at the dynamics, the dynamical system we're looking at, there we go. So this is a dynamical system which is operating on the nodes, just the nodes are connected by the hyper edges. Can you explain again what you mean by the dynamics on this specific node?
Yeah. So what I meant was, suppose the node I itself is, let's say it's an oscillator. It is shifting between black and white. Let's say it has an oscillation of that kind. Suppose I add that to this term of its evolution in time. So would that change anything, or is that part of the later part, the time varying thing?
So the time dependency that I will come to now is a time dependency of the topology, not like an additional dynamical system which is operating on some nodes. So I haven't considered that in terms of like an external input or something like that. Maybe if you mean something like that, I haven't considered that. So basically the nodes have an initialization and then are evolving in the dynamical process, which is specified by that function, and there's no like external input or something like that, which is influencing individual nodes, something like, no, I haven't considered that. But that's an interesting idea for sure.
Thank you. Yeah.
You're welcome. Any other questions for now? Okay, if not, I will turn over to the temporal case now. So consensus dynamics on temporal hypergraphs. Yeah, the motivation behind that is simple. In a number of application scenarios, may it be animal movement patterns or contact networks derived by phone calls or transportation patterns and opinion formation in social networks. We are interested in understanding a dynamical process which is taking place over a time-varying network structure. So such systems can often be modeled as time-switched systems, for which something like a switching signal selects an interaction matrix from a set of matrices for any point in time. And then this matrix determines the evolution of the node state vector for that time frame. So as you already asked before, we're looking at a time switching topology here now. And the form of the operator is determined both by the type of dynamics, so if it's diffusion, consensus, synchronization, or whatever, and then also by the topology of the possible interactions. And in the case of pairwise topologies, this would be a temporal network, but we have seen in the part before that multi-body topologies can heavily influence the dynamics on the network already. So the question is now, how does that interact with the temporal ordering? So what is possible higher order effects of temporal interactions? Temporal ordering can influence the dynamics, which is true for temporal networks, as I already said. but also for more general topologies such as hypergraphs. And I just want to give you a small example where that might be coming from. So in this example, in the temporal topology on the left side, only the indirect interaction I to P is possible, in this case via two possible temporal paths, which are visualized by the red arrows. But the backward flow of information, so from node P to I, which is visualized by the blue arrow, this is not possible due to the temporal ordering of the interactions. And nevertheless, if you look at the aggregate topology, which is often analyzed in the analysis of temporal networks, both of those indirect interaction paths are present. So that's a problem, obviously, like that might change things in the analysis if you just look at the aggregated topology. And in this part of my presentation, I want to combine the two research strands of higher order models of temporal and multi-body interactions and investigate time switch dynamics evolving over temporal hypergraphs to see what can happen of these consensus models on temporal hypergraphs. Okay, so we now want to extend the previous consensus model, which I've introduced from static to temporal topologies. So now we are dealing with a sequence of adjacency tensors. And based on this switching topology, the dynamics in each time windows are now defined by the corresponding Laplacians that I've derived before. And as those are node state and also thus time dependent themselves, an analytical treatment becomes very tricky now because the operators themselves change during time. And therefore, to start, we now first focus on the treatment of the linear dynamics. So we then have motive Laplacians in each step, and which then capture the interaction topology of the hypergraph, as I described before. So we want to compare the temporal and the aggregated static dynamics, and we restrict ourselves to study the effects of the temporal behavior over one time window tau, and the effects of a specific ordering that we assume in that hypergraph in this window is then drawn at random from a multiset of Laplacian matrices. And the expected outcome of the random sequence after one time period is then given by this first equation. And we can compare it to the outcome of the time aggregated hypergraph with the expected outcome of this random temporal hypergraph after a period tau. I won't go into the mathematical details here. You can read that in the paper, but we can analytically derive through this relationship a relationship of the spectra of these two matrices, which then enables us to compare the spectral gap of the two systems. And that's cool because that quantifies the relaxation time of the system. So what do we want to particularly look at now? We study this for synthetic systems with groups which consist of D nodes, and they interact jointly in each time window. And we focus on two scenarios. First, we consider a system with pairwise interactions, which is represented by a simple graph consisting of a clique comprising those D nodes in each time window. And yeah, that's simple. We know what that does. The consensus dynamics then are simply given by the negative Laplacian of this motive. And the second case, we consider a setup in which the system is described by underlying three-way interactions. And due to the linearity of the dynamics then just are reduced to an effective weighted graph, as I showed in the first part, which is represented by the, motive Laplacian, which then captures how many three edges an edge is part of. So the functional relationship for the temporal and aggregated interaction matrices then allow us to compare the spectral gaps of these systems, as I already said. And we can see that temporal dynamics are always slower than the aggregated dynamics, independent of the group size for both pairwise and three-way systems. And moreover, the dynamics converge for small time windows to the aggregated dynamics. And interestingly, the slowdown effect is stronger for three-way interactions for D bigger than 3, which is scaled by the nonlinear function alpha. So the dependency of the group size And that function basically leads to a nonlinear dependency of the higher order temporal effect on the group size, which quantifies an interaction effect of temporal and multi-way higher order effects, even already in the case of linear dynamics. And that's cool because if you remember in the first part, in the static part, linear dynamics really were just rescaled pairwise dynamics. And now we have this interaction effect in convergence speed already for the case of linear dynamics. And we can also analytically look at it. Okay, so let us now look to the more interesting case, the nonlinear dynamics, and see if that does something with the consensus value as well. So if you recall, the interaction matrices are now state dependent due to the nonlinearity, and that makes analytical treatment unfortunately very hard. So we will now investigate the effects based on simulations. And as a recap, before we have seen that temporal and aggregated systems differ already in their convergence speed in the linear case, but that did not have an impact on the consensus value. So for a nonlinear consensus, we've already seen in the static systems that that has an impact on the consensus value. So you could observe shifts there, which would not be present in a network setting. So yeah, we'll see what that does in the temporal case now. And for that, as I told you, we are looking at this clustered setting again. So in that case, we already knew that if we had all of the three edges oriented towards one or the other cluster, there were shifts and either one or the other cluster dominating. So we now are looking at the interesting case when p is equal to 0.5. So if an equal amount of triangles are directed towards A and B, so basically the connection is balanced. So if you remember, that did not lead to consensus shifts in the static case, or just because of like a random distribution of the triangles, but it averaged out over many simulations. And just in order to motivate this setup in a temporal way, which I will introduce now, just consider a setting in which maybe two parties are debating about a certain issue. And then members of each of the parties are all in contact with each other, but across party lines, not all people are debating with each other, but instead there are maybe certain subgroups of representatives which are meeting to discuss. And those are then the connecting three edges, which involve members of both sides. And even though the overall oriented edges are balanced and no group has an advantage, in every of those connecting three edges, one party still holds the majority. And we then call those subgroups, for example, if A is the majority, a majority subgroup. So what we are looking here at now is a first mover A scenario, which means that first of all A majority subgroups interact for some time, as you see in this picture there on the left. Then all B majority subgroups interact, and then the whole hypergraph interacts in order to reach consensus. And we compare this then with the temporal, so this temporal sequence with the aggregated static topology of just the whole hypergraph. Okay, let's first look at the results for the aggregated system. So in the linear case, there's a perfect conservation of the initial mean. So the aggregated nonlinear dynamics show a small shift due to the locally different clustering of the three edges, but more or less it's balanced out. But if we now consider a first mover A scenario, the linear case still conserves the mean, but there's a huge shift due to the temporal ordering of the subgroups, which then leads to a first mover advantage of group A. And if you try to get, I'm just trying to give you a little bit of intuition why this happens. So if you have an average opinion in the majority A subgroups is dominated by group A, obviously. So that leads to a nonlinear shift of the average opinion towards the initial states of group A first in the first window. And then basically, due to the temporal ordering, group B doesn't have such a strong influence anymore because they were already influenced by group A before. And that's why the nonlinear influence of group B in the second time step isn't as strong anymore as group A had as this first mover advantage, basically. Yeah, and therefore the consensus value is mainly influenced by the first mover group A. And if we consider the opposite scenario where the B majority subgroups interact first, the shift occurs exactly to the other direction. And again, in the linear case, you wouldn't see anything. To investigate that more systematically, we computed the final consensus value averaged over 10 simulations. And I think this first, so the error bars display standard deviations. And yeah, the value P, you already know that. And what you can see there is basically that as the fraction of 3 edges directed from cluster B to cluster A increases, so does the consensus value towards the initial state in cluster B. And that's the same effect as we have seen in the static case, but that effect is now reinforced by the topology if the first mover group is the same as the topologically dominating group. So for P smaller than 0.5 and first mover A, that's the blue line, that is reinforced, and the other way around for the other groups. And you can also see that the rate of convergence is significantly faster when the initial configuration is very asymmetric. So for values of P in the center, for extreme values of P. And moreover, the convergence is sped up if the orientation of the 3 edges and the first mover groups align. So that's a convergence speed result as well. And additionally, we can see that for shorter timescales of the interaction, so if you let each time window, you decrease each time window, so they're just interacting very shortly, the temporal networks converge to the aggregated dynamics. So that's a more or less equivalent result to the first linear case where that convergence also happened. And now we can observe this convergence in the simulations as well. Okay, so let me give you the key messages of the second part. We have investigated consensus dynamics on temporal hypergraphs now, combining 2 research strands of higher order models with temporal and multi-body interactions. And we found that in the linear case, the convergence speed of the system can differ. So we specifically found that the convergence of a time-varying system with multi-way interactions is slower than the convergence of the corresponding system with pairwise interactions. And that again then is slower than the corresponding static network. And we find also that in addition to an effect on the convergence speed, the final consensus value is also impacted by temporal ordering and can differ strongly from the consensus on the aggregated static hypergraph. And in particular, as I've shown you on the slides before, we can observe a first mover advantage in the consensus formation process, which would not be present in a static system. Yes, that brings me to the end. Thank you for your attention. And to end this presentation, I think I would really like to thank all of my collaborators for the great work on these projects. And there's all of the references for the first and the second part. And there's also the further reading of the generalization to general hypergraphs, if you're interested in that, or there's a book chapter that will, I think, appear soon, but is already in archive, which summarizes all of that. And thanks a lot for your attention, and ask all questions that come to your mind.
Thank you very much. Thank you, Leonie. So if there are questions from the participants, of course, I'll give priority to the participants, and then I might have a few questions myself. So any questions from? Oh yes, please, absolutely.
Hi, Leon. This is Sneha again.
Yeah.
Just a very silly question. So when you say that the system has it converged to a state, you mean that the nodes have reached a collective state, right? Either it is the black or this thing. So at the end, every node has the same state.
Exactly, but it's not black or white. So this is continuous dynamics. So we don't have discrete states, just 0 and 1. But so the consensus value on an undirected network, for example, with initialization between 0 and 1 would always be 0.5 then. So it's continuous node states.
Okay, but the state that every node reaches is the same, whether it's 0.5.
So that's consensus then, and we're like making it be consensus all of the time because of so the operator is always positive definite if we have monotonically decreasing function there. So that's why we always reach consensus. The question is just where in our model.
Yeah.
So there
that
we also
sense.
did in the so if you want to read the paper for the static case, we've also tried out the Heaviside function, for example, as an influence function s of x. Which then would be something like, okay, we either talk to each other and then in a linear way, or we don't talk to each other at all. And then you can think of scenarios where there's actually no consensus reached. But yeah, if you take the exponential function, which we usually did as a monotonically decreasing function, then convergence works.
Yeah, that's what I was thinking, because that might be some patterns would be forming in some scenarios when you don't have this monotonic function.
Yeah.
So yeah.
Yeah, exactly.
Very nice talk.
There's
Thanks.
scenarios where that wouldn't work, and sometimes it makes sense, I think, to think about other functions that you could take there.
Yeah, there could be also like waves of opinion. Like sometimes it happens, like waves are going around, and then in terms of opinion, just like in a stadium when you see some waves of people shouting, that kind of scenario can also happen.
Yeah,
anyway,
exactly.
That's different.
Yeah. So actually, in the work with Rohit Saras-Rabude, the one where we also generalized this to general hypergraphs, we took some scenarios where we try to get motivation from social judgment theory and created a function which basically had these cutoffs of like I'm either not talking to you at all or I'm very much influenced as like some kind of a Heaviside function, which then has interesting results because you always have some kind of stubborn nodes which wouldn't change their values at all. So that's like variants of the model that are definitely interesting if you change those functions.
Thanks.
Thank you. Are there any other questions from the audience? I think there is a question from Adam Antius.
Yeah, hi, very nice presentation. Just a quick question. What triggers, how often do you update your graph and what will trigger the update?
Can you repeat that? My internet was stuck for a second.
Yeah, really sorry. How often do you update your graph, the weights and the whole process of, you know, the interconnections between the nodes, and what will trigger that update? Because you can't have a stale, I guess, graph based on new information. So I guess you need to update the graph. What will trigger?
Do you mean in the temporal case? So when the interaction topology changes?
Yeah, exactly. I mean, what will be the signal to update that graph? Because I guess if you have smaller changes, what's the point to do all of that pipeline of calculations between all of the nodes? Even temporally, because I don't know what you mean temporally, like how many nodes should be there, only 2, or like a cluster of nodes, for example. I'm trying to understand the thresholds and to make it more live somehow, the network, not like stale.
Okay, I'm not sure if I understand the question right. So in this scenario here, in the temporal case, I only updated it 3 times. So for exactly those 3 time slots that I showed there. But it's obviously a very synthetic example, which is just supposed to show what can happen if you have those extreme cases of just like this first mover A scenario, for example. But you could obviously extend that to any kind of temporal hypergraph that you have. So if you have information, for example, if you have data, like I don't know if you know the socio-patterns data set, that's like a data set where you have interactions between people in a conference, and then you have snapshots of that hypergraph for different time windows. And you could simply take those snapshots as the interaction topology for each time window and then just simulate the dynamics on that. And that would then, be the time switching topology in a real world scenario, for example. Does that answer the question?
Yeah, I mean, you mentioned in the beginning that you would like to do something in finance. So because I'm doing something with extreme events right now, so I'm trying to understand, practically speaking, what can trigger an update. So what will be the indicator?
Okay, so So I'm looking more at the dynamics on a time evolving topology, and there's no feedback on the temporally evolving topology. That's why, so the dynamics basically don't trigger some kind of change in the topology in my model case here. So basically the time switching topology is already there. So I either assume it synthetically or I have data about it or whatever, and then I'm simulating the consensus process on it. There are also models which basically where the dynamics trigger or like influence the temporally evolving topology. So that would be some kind of a feedback loop then, but that doesn't appear in this model, if that may be.
Yeah, thank you very much. Thank you.